What are the odds that a no-name 18th century Presbyterian minister held the key to making artificial intelligence a reality? While Ben Franklin is running around flying kites, Thomas Bayes is figuring out how to make educated mathematical guesses in situations where you don't have that much to go on, like possibly the probability that this guy exists. But then Bayes dies before he's had a chance to tell anyone what he's been up to. Soon after, his philosopher buddy, Richard Price, discovers Bayes' notebooks while digging around his apartment looking for free swag. Price is a pretty smart guy, so he instantly recognizes the genius of his pal's theory. In 1763, he cleans up the math and publishes it in an obscure journal before using it to revolutionize the insurance business, where they need probabilities to figure out how much to rip you off by. Fast forward to 1812. While the US and England are at it again, a French guy named Pierre-Simon Laplace develops Bayes' theory into something more usable, which becomes known as conditional probability. It lets you update your guesses with any new facts that might come your way, like this. Say the probability of getting dengue fever while visiting Bermuda for a week is 1 in 10,000, or 0.01%. I'm totally making this up. You go to Bermuda, come home, and to be safe, take a test that is 99.9% accurate in detecting the virus. Your test comes back positive. You start to freak out, saying goodbye to loved ones, writing out your will, and are about to adopt a new religion when you take a second Bayesian look at the results. Remember, for every one person with the virus, there are 9,999 people without it, which means that even a robot programmed to always spit out a negative test result, regardless of who's taking the test, would still guess correctly 99.99% of the time. Being accurate 99.9% of the time, then, isn't really that impressive. What you really need to figure out is how accurate that test is when it spits out a positive result. When this one person with the virus takes a test, chances are 99.9% that it'll be accurate. Out of the 9,999 people without the virus taking the test, 99.9% of them will get an accurate test result, which translates to 9,989 people. That means that the remaining 10 people will be inaccurately diagnosed, testing positive for dengue fever when they don't actually have it. So, out of the 11 people testing positive for the dengue virus, only one of them actually has it, meaning the chances your positive test result is right is only 1 in 11, or 9%, not 99.9%. Now swap dengue fever with HIV, and you're looking at an actual, real-life example people have found themselves in. Conditional probability works pretty well, and can literally save your life. But the big thinkers of the day aren't impressed with the phrase, works pretty well. They're all about frequentist probability, a more popular approach that claims that the only way you can really know the odds is to have lots of hard, objective data that backs you up. Let's say you flip a coin once and it lands heads. Based on that, you might assume it's always gonna land heads, but that'd be pretty stupid. We all know that the more times you flip a coin, the closer it's gonna get to landing heads just half the time. That's the whole point of frequentist probability. Flip that coin enough times and you'll have good enough data to take on Vegas. To those guys, Bayesian probability is like shooting an arrow half blindfolded and hoping you hit the target. But most of the time, that's exactly where you find yourself, needing an answer without having much to go on. That's why World War II hero Alan Turing, that nerdy British guy who dreamed of computers way before Steve Jobs did, used Bayesian probability to crack top-secret transmissions, some of them sent from Der Fuhrer himself. Despite this, the frequentists still think Bayesians are lame, and the rivalry continues deep into the 20th century. But then, the 1980s. People had been trying to make artificial intelligence a reality since the 60s, programming computers with basic logic like, if X is true, then Y happens. That approach works fine as long as X is always true, but as you can guess, there are too many unknown variables in the real world to bring C-3PO to life. But then, in 1988, Judea Pearl jumpstarts AI with a new approach based on, you guessed it, Bayes' theory. So that's why in 2011, when a computer called Watson beat a couple of humans answering questions on Jeopardy, it was Thomas Bayes running around inside Watson's brain going, if this is true, then that might be true. And if that other thing is true, then I'm gonna buzz in with, what is Chicago, Alex? 250 years after he flipped his last coin, it turns out Bayes' odds were pretty damn good.
I'm John Hockenberry, yes indeed, and as that movie tells you, we're going to talk about probability today, and you guys all know about probability, right? I mean, probability, what's hard about that, right? We live with probabilities every day, yes? Huh? Come on. I mean, what's the probability that you're going to catch this, huh? What? Ooh, 100, nice job, excellent. How about you? Was that random? I don't know. Was that random? No, I actually knew I was going to throw it over there, but it was unknown who was actually going to get the ball. So anyway, probabilities, we love probabilities, and as the film told us, here at the World Science Festival, we've discovered once again that the 80s were like the 1700s, and that anybody who tells you that they're 99.9% certain about anything is full of, ooh, bad catch, how about over here? Ooh, oh, bad throw. Oh, what is the probability after winning every single one of their decisive Game 7s that the Rangers would win one more last night? That probability is 0. Yes, indeed. I have 2 sets of twins, 3 girls and a boy, and people like to say, you know, whoa, you have 2 sets of twins. What's the chance of that? In my house, 100%. Catch, there we go. All right, I got a set of dice here. Call him. 9. Who said 9? Stand up. Stand up. Who said 9? Stand up. Oh, upstairs. Nice. Yeah. Oh, probability that I know that anyone's upstairs. 0. Yeah. All right. So probability is what we're going to be talking about today, and we're going to have so much fun, and we have so much content to get through, and it's going to be so absolutely fabulous. And one thing I want to tell you about our participants, they know so much about how probability works, so much about just the nature in physics, in medicine, in computing, in mathematics, and physics about how probability works, that any of our presenters, if they're caught in Las Vegas, they get arrested and escorted to the airport. That's how sophisticated they are. One other probability I want to mention here, what is the probability that any of the people up here, now that Polly has left with that fabulous introduction that she did just before the film, what is the probability that anybody up here is not a white male? 0. Something that I assure you all of our scientist panelists want to address here, and something that is very important. We think about probabilities when we think about diversity in education, diversity in science. We want to increase the probability that women are going to get opportunities in science. We want to increase the probabilities that individuals from different places and socioeconomic groups get opportunities in science. So probability suffuses everything that we talk about, and let's begin with our panelists, all right? Our first panelist here is a very lucky guy, senior research scientist at Google, right? There's a gig. Working as part of their quantum artificial intelligence laboratory, his research is leading to new kinds of machine learning algorithms that take advantage of the very nature of quantum dynamics. There's probability for you. Please welcome Masoud Mohseni. Rockstar number 1. Now, rockstar number 2 is a theoretical physicist and a science writer. His book, The Drunkard's Walk, How Randomness Rules Our Lives, was a New York Times bestseller. He also co-authored 2 books with Stephen Hawking. What's the chance of that? Please welcome Leonard Mlodinow. What's the chance I'll get your name right? 0. Leonard Mlodinow. His mom might be in the audience, see, so I got to worry about that. Our next participant is a geneticist and director of the Genome's 2 People Research Program at Brigham and Women's Hospital at Harvard Medical School. His previous work has helped evaluate the effectiveness and accuracy of direct-to-consumer genetic testing services, the probability that any of you are going to be ripped off by insurance companies, right? That's what we were talking about earlier. Please welcome Robert Green. Dr. Green. And finally, the Chief Technology Officer at Universal Robotics, our tallest participant today. He's an Associate Professor of Electrical Engineering at Vanderbilt University, was previously a member of the NASA Robo-naut research team. Please welcome Alan Peters.
Thank you. Thank you, John.
So, gentlemen, how lucky do you feel here?
Very lucky.
Pretty lucky? Pretty lucky? All right. I feel very lucky, and I'm really having all kinds of fun here. Let's talk about, right off the bat, the most sophisticated and I think, in some sense, the most exotic example of probability in the world that we inhabit. The quantum notion of probability. The idea that in physics, what was discovered at the end of the sort of relativity era was that because of quantum theory, the subatomic world operates according to probabilities, that things can happen one or the other or simultaneously. How does probability figure in quantum mechanics? And then we'll move on to some of the work that you're actually doing.
I would like to emphasize that the notion of quantum probability it's substantially different from anything that you've experienced in classical world. And to illustrate this notion, I'd like to start with an example of how to imagine a world that quantum probability rules. And this is kind of the domain of the subatomic physics, atoms, molecules, a lot of processes that happens every day. They are ruled by this probability distribution, this exotic feature. So it's not like an abstract idea. It's something that explains why matter exists, why we exist. So the best example to see this, it's what is known as double-slit experiment, is that I want to start with a classical version of it. Imagine that you are given a machine gun and you are sitting in a room. There's a wall and there are 2 holes in the wall, 2 slits. And you just randomly shooting with the machine gun. And there's a screen behind the wall. And someone can look at the screen and see where the bullets are arriving. And so yeah, imagine that each bullet either goes through a slit number 1 or a slit number 2. And so you expect that behind the wall on the screen, you get maximum distribution of the bullets arriving right in behind the holes. But if you replace this with a quantum alternative, which is like you have an electron gun and you're randomly shooting electrons, and each electrons you expect goes either from one of these 2 slits, but that's not true. If you look at the interference patterns that happens in the screen behind the wall, you see that there's a fringes. So there are like a distribution of probabilities that is either goes from 0 to various different peaks. And we have an animation here that you can see that there's going to be like a wave nature of the particle. So each electron essentially behaves as a wave, and that's the only way you can understand it. And in a way, the classical analog would be like saying that the electron goes through both slits simultaneously, and this has huge implication into describing how the atoms and molecules are formed, how they structure, how we have this kind of various diversities in physical world.
Let me back up a second here, because I'd like a job at Google, and so I'm going to work on my interview in this interview with you, so I can sound sophisticated when I actually go out there to be interviewed for a job. What you're saying is in the sort of quantum probability world, there's this wave and particle behavior, right? Is that the equivalent of heads or tails in flipping a coin? Is that the equivalent of ones and zeros in the different states that we talk about in, say, computing? Or is that something fundamentally different?
The wave-particle duality is coming from different aspects of seeing a quantum particle or experiencing it based on observation. So in each given experiment, we can either focus on the wave nature or particle nature of the quantum entity. But the 0 and 1 is described by two different states of, for example, an atom. An atom could be either ground state or excited state. So when it's at the superposition of this ground and state, it's a wave, its electron is as a wave that can occupy certain radius from the center of the atom. And that's kind of being superposition of 0 and 1. And that you can encode information and do like something that, called, quantum computing.
So there's this magical state that is based on quantum theory that as long as you don't look in the box here, there's the possibility that a particle or an entity can be in two different states simultaneously, right?
Yes.
And in that threshold of simultaneity called superposition, right, a whole lot of wild, fantastic stuff can happen.
So, the concrete way of looking at it, like, assume that you are going to New York's public library and there is someone is marking one of the book in random. So assume there's just 1 million book. I think more than there are 50 million, but for the sake of this example, assume there's 1 million book. One person marked the first page of one of the book and put it in random, and it says find it. So what are the odds to find it? How many times you should try it? It's on the order of the number of books. So if there are 1 million books, you have to do 500,000 in average. If there's a quantum person, in a way that he can become like a 1 million person, go in superposition of all various states that each state represent to looking up one of the book. And in a virtual world can exchange notes, all this 1 million person can exchange notes, and then when coming back to the reality, they know what this book is. And this is, you have to do it on the order of 1,000 try to find a book. So it's a quadratic speed up, and this is provable speed up known as quantum search, which is it's exploiting this parallelism in quantum world for computation.
A lot of people are familiar with. How many of you are familiar with the Schrodinger's cat problem here? A lot of. So how does the familiar Schrodinger's cat construction and problem illustrate what you've just been talking about?
So Schrödinger cat was proposed by Erwin Schrödinger, one of the founding father of quantum mechanics, in 1935 in response to an article by Einstein, EPR paradox. And he wanted to illustrate the exotic nature of quantum mechanics. And he was saying that, if you have one of these atoms can be excited or not excited, that essentially an atom that is excited could radioactively get excited. And that's kind of a probabilistic event. You never know when it's going to happen. And when that happens, can trigger a mechanism in a counter, a Geiger counter, and release some gas. And if you have a cat in a box with that kind of gas that is being released by this probabilistic event, then the cat could be in superposition of dead and alive if we don't know the atom is excited or not.
As long as you delay the measurement as long as possible, you have this superposition state of where simultaneity can occur. And you can take advantage of that. And our next slide shows how you guys over at Google are trying to take advantage of that. What are we looking at here?
This is a dilation refrigerator, which is this is a device to bring down the temperature of the chip to below the critical temperature, allows for superconductivity. And then the actual chip is an array of superconducting electronics, as I mentioned. These are like ring of that each one encodes 1 bit. This is a particular chip that was produced by D-Wave, a company that was leased by Google, and we are experimenting with it.
And what can a quantum computer do that a classical computer cannot do in the best case scenario, even though we are at a fairly theoretical point now?
So as I mentioned in the context of search, a quantum computer can search from an unstructured database quadratically faster. And this is a provable speed up that has been shown. But there is an algorithm for factoring large prime numbers into prime factor. This is Shor's algorithm, which is exponentially faster. But there are other algorithms that we develop for doing quantum machine learning that you can use a quantum device for optimization and inference, essentially coming up with better solutions to this kind of hard optimization problem known as non-convex problem that has a very rigid landscape. So it's easier to generate probability distribution that captures those kind of highly rigid landscape than a classical machine.
What is the chance that Google is going to, without telling any of us, put actual liquid nitrogen in our smartphones that could possibly run in our pockets and freeze our nipples?
I would say zero.
Zero.
Yeah.
Zero. All right. Thank you very much, Mohseni. That's great. Thanks so much. We all have an innate sense of probability. How many have been to a casino? See, I would think this would be a very small casino crowd, but actually it's a lot bigger than I thought. Who did a lottery ticket in the last year? Okay, very good. That's a sign of the state of the economy. There you go. Yeah, right. So, Leonard, we think of ourselves as good, maybe, at calculating our chances at things, and all the time we're sort of calculating probabilities. The film at the beginning of the program talked about Bayes and the frequentists and the calculations that were used really 250 years ago. And how do they represent the same strategy or a very different strategy than what we use today to calculate probabilities?
Well, actually, the scheme that Bayes came up with is still used today. We've gotten more sophisticated with how we use it in the situations that we use it in, but it's mathematics, unlike physics, which remains true with
Who's good
time.
at it? Banks? Are they good at it? I guess excluding 2007.
Are the banks good at it?
Yeah.
I try to keep my distance from banks, so I'm not sure.
And in terms of the applications to our daily lives, there are probabilities being calculated way beyond simply the insurance industry. It's happening constantly. The algorithms that we see on search are all related to probabilistic phenomena.
Well, sure, because companies that are collecting, probably like Google, who are collecting all their data on you, are calculating your probability of reacting to certain ads, of desiring certain products, of behaving in certain ways, and Bayesian statistics is very important for that. So they know where you're going to dinner after this, by the way.
Yeah, right, I know. Yeah, I haven't even figured it out yet.
But that's the point.
Yeah, that's the point.
Ask Google's an app for that. You can just ask Google, where am I going?
So let's, in a real-life situation here, that you may have figured out World Science Festival, man. It's Stump the Moderator. That's what we do here at World Science Festival. We're going to have a real-life example of something that some of you may be familiar with. How many know of the Let's Make a Deal program on television? How many of you remember television? Yeah, right. Okay, Let's Make a Deal was this sort of thing where you'd get up and you'd try to guess the price of things, and you would evaluate your own probability of whether your price guess was right, and if you won prizes. But then there were always this, at the end of the game kind of thing, and you would squeal, and you would dress up in very interesting costumes. And at the end, they would play this game where you'd try to pick something behind 3 doors. And we need someone to play for us here. Let's see. How about you in the red shirt? Come on up. Come on up. Excellent. You realize that you could win a car today. Here's the microphone.
Or a picture of a car.
Yep. Stand on the X. Stand on the X. Hey, don't give anything away here. All right. So here we're going to play the Monty Hall game. In this game, you're going to have to pick one of 3 doors, and behind one door is a car, okay? You're not actually going to win the car. All right, let's just say that. What's your name again?
Lauren.
Lauren, let me see, I'm no good as Monty Hall. Lauren, pick a door for us, won't you?
Door 3.
Lauren picks door 3. All right. Lauren picked door 3. We've eliminated one door, so Lauren is probably feeling pretty good. The car was behind door number 2. How are you feeling, Lauren?
Feeling good.
That's how you feel good?
Oh.
What are you majoring in at NYU, by the way?
Social work.
Exactly. Okay.
Good, because we need it here.
Yeah, we do.
I think you should say that. So after you pick door number 3, Monty Hall, who is the host,
Don't tell what Monty Hall's going to do.
he did it already.
He did it already. He eliminated number 2.
Well, that's what I want to say.
So what was the probability that you could win the car the first time around?
Okay.
What was the
1
probability?
out of 3.
1 out of 3, right. So what has Monty Hall done now, Len?
What Monty Hall did was he
messed with
said,
your
you
head.
picked door number 3, so I'm going to open a door, one of the other doors, to show you what's behind it. And that's what that was, okay?
Right.
Yeah.
So
now you're asked, did you ask already? Or?
I haven't asked already.
Do you want to
so,
ask?
So you have the chance, Lauren, to stay with door number 3 or to pick door number 1. What are you going to do?
I'm going to stay with 3.
You're going to stay with 3. Why are you going to stay with 3?
You guys know too much.
Oh, come on. Why are you going to stay with 3? Lauren, why are you staying with 3?
It's my favorite number.
It's my favorite number. Yeah. So you're not in the sciences. You're majoring in social work. Okay. All right, great. Let's see what's behind door number 3. Oh. You lose, Lauren.
You lose the car.
Sorry, you lose the car, but we...
I would say bad
yeah,
symbolism.
thank you very much. There's a parting gift for you. It's a Maserati parked outside the front. Let's hear it for Lauren. All right, this is actually a classic problem, Len, called the Monty Hall problem. All right, in probability. Explain it, lay it out for us, and why did so many people in the audience boo when Lauren, or not boo, but encourage Lauren to change her pick, do you think?
Because, okay, if you're a virgin to the Monty Hall problem, you probably think, why would it matter if I change or I don't change? Because the chances that I pick the right curtain are 1 out of 3 either way, right? But if you've heard of the Monty Hall problem, you know that it's better to switch. Your chances are doubled if you switch. So why don't we illustrate why that happens?
How can that be true? How are the chances double if you switch?
Oh, look at that. We've got it. So here's the situation without the curtains.
Okay.
Okay, when you come up to pick, there are 2 possibilities. One is that you will pick the curtain with the car, call that the lucky guess scenario. You pick the curtain with the car. And the other is that you picked one of the booby prizes, or the, I guess, zonk prizes.
Right.
And that's either one of the other curtains. Now, the chances that you were correct and you picked the car were 1 out of 3, obviously, as you can see from this, from this. And the chances that you picked a booby prize are 2 out of 3.
Right.
Okay.
Got it.
So, suppose you're in what we call the lucky guess scenario, and you picked the car to begin with. Of course, you don't know that. Then Monty Hall comes up and says, "Okay, you picked number 1, curtain number 1, and I'm going to open one of the other curtains, and let's see what's there." And then Monty just picks one or the other at random because they're both essentially identical, and he'll open one or the other. So that doesn't change anything. It's still everything that's going on is random. And now what's left is you've picked the car, and the other curtain is not the car. So if you switch at this point, you lose, and if you stay, you win. So it's better to stay in this case, correct? Okay. Now, let's look at the other scenario, which we call or at least in the Drunkards, my book, I called it the bad guess scenario. So that's the...
good guess scenario.
That's the bad guess scenario.
All right, so, okay, we're moving on to the bad guess
Moving on to the
scenario.
bad guess scenario.
Yeah,
So you picked one of the zonk doors to start with.
Right.
Okay, now let's see what happens next. Now Monty comes and says, "Okay, you picked curtain 2 or you picked curtain 3, and I'm going to open one of the other curtains to, let's see what's behind that curtain." But now what Monty is doing is not random at all. Monty is avoiding opening the curtain with the car, because to open the curtain with the car would end the game, and that would be a dud. So Monty does not open that. So it's no longer a random process. Monty chooses to open the curtain with the booby prize that you did not pick. So he's injecting new information into the system. Okay. And in this case, what happens? Okay, you've chosen a booby prize. He's opened the other booby prize, and now if you switch, you win, and if you stay, you lose. So the optimal strategy is different depending on how you started. But the chances that you're in the bad guess scenario are 2 out of 3. They're twice as great as the chances that you're in the lucky guess scenario. That's where it's better to stay. So if you switch, you'll win twice as often as if you stay. And that's why it's good to switch. And apparently, most of you all know that, right? Okay, so
that's why Lauren should have switched.
that's why she should have switched.
All right.
But
so,
sometimes we think we have a hunch, and we're just going to stick with it.
Yeah. And partly that's what goes wrong in our kind of mythology about probabilities, is in that we hear the zonk, and we feel like we're lucky, and we're on something of a hot streak, and we don't calculate objectively what's going on in the system, and so we stay with our guess even though it's against our interests.
Yeah, and you know what, and suppose that she had picked that and she had been right, then she'd walk away going, see, I was right. And see, that's the thing about probability. It's only true in the long run, right? In any particular case, you could be better off to switch or not to switch. And so you can't say that one instance of this proves anything. I was once walking by a slot machine, and someone was feeding dollars into it, one after another, really fast. I guess it was this person seemed to be addicted to it, right? Put it in, keeps losing. As I'm walking by, his wife says to him, keep going, you're due. I'm thinking to myself, you don't know anything about probability, he is not due. And then, bing, 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 he won the jackpot. I guess he was due, but no, had I said you're not due, other than in my head, I would have been embarrassed then. But
obviously the fact that you walked by was the reason he won.
That must be it.
Yeah.
So, by the way, for a fee, I will do that for you in New Jersey.
Excellent. Very good. All right, let's look at another problem. And it's really all about, again, our gut, what we think of as the probability that seems obvious to us, but when we look at the system and look at the information that's actually in the system, it's a very different approach, and
right, and this
doesn't
is
feel intuitive.
What his theory was all about. It's what happens to probabilities when you add information to the system, and how do you revise them?
All right, so this is the girl named Florida problem that I want to look at.
Girl named Florida problem.
Girl named Florida problem. This is famous. I mean, I'd never heard of the girl named Florida
It's
problem. I don't
famous
know a girl
because I
named
put
Florida.
it in the Drunkard's Walk in my book.
All right, great.
And you've all read it, so they all know it.
The book named Drunkard's Walk, available at your local bookstore.
At your local bar.
Yeah, there we go. Okay, so girl named Florida problem.
So this is actually an obscure problem that I heard about while I was writing the book that was being passed around in Eastern Europe somewhere. And it's a very counterintuitive problem. But to appreciate the problem, let's start with another problem, which is a famous problem in any probability class, called the two-daughter problem. Who's taken a probability class has seen the two-daughter problem?
Clap if you've done the two-daughter problem.
All right. So there we go. That's
clap
the two-daughter.
If you have two daughters. Okay, there we go.
Wait, you say clap. Clap if you have two kids who are both daughters. Clap if you have two kids, one of whom is a daughter. Was that about twice as much? All right. That's the point. So if you look at this graph here,
all right.
This shows the possibilities if you have two kids. The first kid could be a boy, and the second kid could be a boy.
That's the BB.
BB, that's on your left. The first kid could be a boy, the second kid could be a girl. The first kid could be a girl, the second kid could be a boy, or girl. So to solve these simple probability problems, we just write out what we call the sample space. So these are all the different possibilities. And to make it concrete, I like to think of this as in real numbers. So let's say we have a village with 4,000 families in it, and let's see the next bit. So if you had that village, keep going. Keep going. Okay, stop. So now that's how it would play out. You'd have about, if the statistics match the probability, you'd have 1,000 of each of these situations, right? Now, the two-daughter problem says, suppose if you have a family with two kids and you know that at least one's a daughter, what are the chances that both are girls, okay? So how do we figure that out? Well, we look at this village with these four possibilities and we say we have added information. The fact that one or more kids is a daughter is extra information. In fact, it allows us to eliminate now the upper left square.
BB.
So let's eliminate that.
Okay.
The boy. Goodbye. Okay, now this is the village that's left. Once we add that information, we're restricting ourselves to just these families.
We didn't do anything to hurt the boys, did we?
Yeah.
They're fine.
I think they're okay.
Okay, all right.
We
all
took them to Disneyland.
I'm
no,
a
not fine.
journalist.
then.
I have to ask. You know.
So we have these 3,000 families left, and how many of them have two girls? 1,000 of them, right? So the chances of, that both are girls in this case is 1 out of 3.
So if you know that one is a girl, the chance that any family has 2 daughters is 1 out of 3.
Right.
Excellent.
And this is how we get to it. That's what you do in elementary probability class. That's called the two-daughter problem. Okay, so now let's look at the girl named Florida problem. So this is the question in the girl named Florida problem. A family has 2 children, as before, but now we add one little piece of information. We know that one of the children is a girl, not just a girl, but a girl named Florida. And we'll assume that the name Florida is a rare name, let's say 1 in 1,000, okay? So I'm telling you now that not only that one's a girl, but one's a girl, I'm giving you the name. It's a girl named Florida. Now I'm going to ask you the same question. Before we saw that the chances that they're both girls are 1 out of 3.
What's going to be 1 out of 3 here?
Is it 1 out of 3, John?
Of course.
Have I changed it by telling you the name?
Yeah, what difference does it make?
Who thinks that I changed it? Who thinks that I didn't change it by telling the name? Clap if I did not change it by changing the name.
Yeah, you're throwing some noise in there to fool us.
Say what?
You're throwing some noise in there to fool us. The Florida thing is just, it's like a trick question on the SATs.
Clap if you think I did change the probabilities.
Oh, who's clapping so loud? Who's clapping? That's a very self-righteous clap there. All right, go ahead. Go ahead.
Yeah. All right. Well, let's analyze this problem the same way we analyzed the other one, and now let's just move forward. So this is the situation now. In the upper left, you'll see there's 2 boys.
Right.
Now I've subdivided the girls into a girl not named Florida, which is just G, or a girl named Florida, which is an F. So as you'll see, the lower right set of 4 squares, those are all the 2 girls.
Right.
There's a case where they're both girls. There's a case where they're both girls named Florida. There's a case where the first girl was named Florida, and there's a case where the second. And since it's a 1 in 1,000 name, out of the 1,000 families that we had before that had 2 girls, now there'll be one family that has the first girl was named Florida because it's 1 in 1,000, and there's a family where the second girl is named Florida. And then there's a case where the parents are really nice and named them both Florida. But since we're assuming that this is all independently of each other, and since it's 1 in 1,000, the chances that they would randomly name them both Florida is 1 in a million. So we'll just call that a 0.
So you're getting rid of that one.
So we get 998, 1, 1. Okay, and then on the blue and the purple are the cases where there's first a boy and then a girl, and there's first a girl and then a boy, and then I divided those up also to the ones that are named Florida and not. So now if we had that village of 4,000, it would lay out like this. So based on the data that we were given, and now we have that extra sentence that says at least one girl is a girl named Florida. So just like before, we incorporate that new information and we look at what's left, and we look at the village that's left. So let's eliminate all these cases where at least one where there's not a girl named Florida, and that leaves us with these. Okay, so these are of all 4,000 families in this village. There were only 4 families that had at least one child who was a girl named Florida. There's the 0, 0, there's the 2 Floridas in the center, but there's 0 families with that situation. So there's 4 families left where they have a girl named Florida. And now let's see how many of those families have 2 girls. Well, there you can see that there's 2, the pink ones, out of 4. So half of the families have, 1 out of 2 families now have 2 girls. Before it was 1 out of 3 had 2 girls. So as you can see, the odds of having 2 girls did change when I gave you the name.
So the addition of the information of the name increases the odds because it eliminates more of the other options.
Yeah, to think of it heuristically, since Florida is a rare name, okay, it's a rare name, and I'm telling you that at least one of the children is a girl named Florida, and only girls have this name, not boys, okay, then I'm giving you a little more information. I'm saying, well, not only is one a girl, but one's a girl named Florida. And in order to have a girl named Florida, you better have a lot of girls because it's a rare name. And so that increases the chances that there are 2 girls. And by the way, you could do this with other probabilities instead of 1 in 1,000. Let's say I just called it P, okay, for probability. So I said the probability of a girl named Florida is that you're going to name a girl Florida is P. So in this case, P is 1 in 1,000. And when P is very small, then the number is about 1/2. Because you notice we made some approximations, like we ignored the two Floridas, right? As P gets bigger, and by the way, I did some research when I wrote the book on this, and there was a time in Scotland where 1 out of 4 girls was named Mary. So this can happen. The name gets very popular. And as the name gets very popular, and in fact, as the probability, you can redo this math with different probabilities P, as that probability goes from very small to approaches 1, where everyone has the same name, and you look at the math, that 1/2 changes, gets lower and lower and lower until it hits the 1/3 of the other problem. So it all works out. There's no contradictions.
We've seen now that at the subatomic level, there are indeterminate phenomena that can be exploited to create all kinds of computing advantages that the engineering of which is very, very sophisticated, but could hold out really mind-blowing opportunities for computing in the future. We've seen how the notions of probability, while they seem sometimes intuitive and simple, actually require a much more complicated look at the complete system to actually make practical use of. For people in medicine, Doctor, what can we do with the kinds of things that we've already talked about to both determine probabilities of medical events and to use probabilities in a way that's not going to terrify consumers? And I have some statistics in a moment to explain this, but I just wanted to hear from you how probability figures into your research.
Well, probability has always been important if you're a doctor trying to treat a patient. If somebody comes in with chest pain, there's a probability they have a stomach upset and a probability they have a heart attack, and you've got to try to assemble the evidence to try to move you in the direction of choosing one or the other. And what genomics has done is invest a huge amount of new information in changing these probabilities, either pre-hoc or post-hoc. So with the cost of genomics coming down and us having genomic information either through medicine or outside of the medical establishment, we now have to sort of think in new Bayesian ways. So for example, it used to be that if you had a family history of a genetic disease, that would put you in the situation, that would be your prior probability of a genetic disease. You'd go to a doctor, that doctor would order a genetic test because you had that prior probability. Now we're actually flirting with the idea, actually more than flirting, we're actually conducting ourselves in a way that uses the genomics itself to create the prior probability. So now we could actually sequence everybody in this audience, and we could pick out the people who are carrying a pathogenic mutation. And then we could ask, now there's a prior probability of you getting that disease, how useful is that to your future health? And
So
that in a
sense,
nutshell is
Mohseni,
my
that's
research.
a little bit like trying to see all of the books in the library at once, right? Isn't it?
Yes.
It's something like that. Okay, great. Let's ask the audience a couple of things. First, how many people feel that they are deluged with probabilities about their likelihood of getting various diseases right now? Clap if you feel that. Okay? And deluged is a pejorative term. Let's just say we're getting lots of information about probabilities and disease. How many people feel that most of this information is useful? Is that to say that you people are sick in some way? Because you know how the probability has worked with you? No. Okay, so you think it's useful. How many think that most of the information is useless? All right, let's take some information which is very well intended about breast cancer. Let's hear a public service announcement that probably many of you have heard.
Hi, my name is Felicity Huffman, and I heart my 6 sisters and my 2 little girls. 1 out of every 8 women gets breast cancer, and someone is diagnosed every 3 minutes. I think we can do something about this.
All right, now that 1 in 8 statistic, and that PSA comes from Lee Denham, it's something that's familiar to you, right? How many of you sort of walk the streets believing, women, that you have a 1 in 8 chance of getting breast cancer? Do you buy that? No one buys that. Well, that's interesting. All right. So the 1 in 8 is a statistical occurrence based on epidemiological data. So if you're looking at all the incidents of cancer and all the women in the United States, 1 in 8 women will develop breast cancer, but there's a piece of information that's missing. 1 in 8 women will develop breast cancer over the course of their lifetime. Now that's true, but it varies dramatically by age. How many of you are in your 20s? Clap. How many of you are in your 30s? How many of you are in your 70s? Couple, all right. All right. So let's take a look at the breakdown by age from the National Cancer Institute. According to the latest information, the odds of a woman in her 30s being diagnosed with breast cancer over the next 10 years are not 1 in 8. They're actually 1 in 227. That's 0.44%. Now that feels pretty good, right? All right. For a woman in her 50s, the odds jump to 1 in 44. That's 2.3%. But you could say that the probability has roughly quadrupled. All right? And that sounds pretty scary. But numerically, it's still just 2.3%. By the time a woman hits her 70s, she's looking at a 1 in 26 chance she'll be diagnosed with breast cancer. That's about 3.9%. And that's roughly maybe a little less than double what a woman in her 50s can expect. Now, how useful are these statistics, Dr. Green?
Well, I think they're really useful for raising awareness. I think that's the kind of shock value that you get out of the first 1 in 8. It sort of galvanizes us and moves us to advocacy, and that's useful. I think the other numbers are useful if you really want to try to hone in on your risk as you get older. And part of the question today is, can we do better than this? Can we actually subdivide those categories into better categories of risk using genetic markers? In fact, breast cancer is a great example, John, because one of the hottest controversies right now is, should people be tested for genomic variants that put them at risk for cancer, such as the one that people have heard of through Angelina Jolie, the BRCA1 mutation. So we can ask our audience, how many of them?
You've done.
Well, yeah, I've had my genome done, and I've looked at all those cancer and cardiac predisposition genes, and I don't have anything for a dominant condition, but I have a couple of recessive traits like all of us do. I actually have in fact, there's a slide of my results from genomic markers, which is not quite the same thing as sequencing, and you can see that I've got supposedly an increased risk of atrial fibrillation, an increased risk of prostate cancer, venous thromboembolism, and so forth on down there. This also illustrates one of the interesting things about how you even talk and think about risk, and it's exactly what you showed in those slides. If you look at that red column that says your risk, that's your sort of lifetime risk, your cumulative risk, if you will. Whereas if you look over at the red column on the right, if you look at compared to average, that's your relative risk. So one of the really confusing things about the presentation of these data is they'll say, oh, you've got 3 times the risk of developing multiple sclerosis. Well, that sounds pretty bad. But if it's 3 times 1%, then your risk is 3%. And that's not very bad at all.
But help me with this. I mean, I look at this chart and it says that your chance of celiac disease looks like close to 0. I mean, you're basically like a celiac-free dude. You're like pretty happy. But it says you're 1.98 times, you're above average?
Yeah, that's a great example.
How can you be above average and so low?
Because by their calculations, it's very, very uncommon. So I might be at twice the risk of someone in the audience, but it's so rare that it's still a very low cumulative risk.
So it's a rare disease, so
Rare
feeling
disease.
good about it is
So
pointless.
prior probability of the disease itself, it's a very, very rare disease, and then the genetics may layer on to that probability.
All right, so now let's ask the audience. Clap, since it's a little hard to see in here, if you would want to have your genome sequenced to answer some questions about your health. Now, as loud as you can, just individually and randomly, and just call out what disease you want to know most about. Just call it out.
Cancer.
Alzheimer's. Heart disease. What else?
Cancer.
What? Cancer. Okay, great. Anything else? Parkinson's. Schizophrenia. Okay, great. Now, I want to know about all of those. My kids think I have some of those, actually. How much help can doctors be with probabilities of some of the things the audience has shouted out here?
Well, I hate to sound like the quantum guy, but a lot and almost none at all. Because
What you've just heard is the sound of a cat that is both dead and alive.
right. Because if you are one of the, let's say, 2% in this audience that's carrying a very highly penetrant mutation for one of the rare forms of these conditions, rare form of cancer that's very heritable, rare form of heart disease that's very heritable, you probably would want to know, you probably could get that information, and it could probably help you avoid the disease. But there's a lot of potential confusion because the rest of us will get probabilistic information, like what you saw with those genetic markers. You'll get the information that you're a little bit above average or a little bit below average. And the experts are really debating whether that's going to help you or just confuse you.
I mean, it's a little knowledge is a dangerous thing.
Yeah, and it's the question of, we have this enormous narrative of determinism in genetics. We have cut our teeth on the low-hanging fruit in genetics, which was the highly penetrant diseases. Huntington's disease, you get the disease if you have the mutation. PKU, you get the disease if you have the 2 bad copies. All those early diseases we discovered were definite things, but most of the diseases in genetics and genomics are actually highly probabilistic. They're risk markers, and that hasn't penetrated our psyche. It hasn't penetrated the psyche of doctors. It hasn't really penetrated the psyche of the audience.
Well, let me push you on that, and then I have a question about all of this for Mohseni, because I have a feeling he's calculating here how his machine at Google could actually help with some of this. You said that we're conditioned to think of genetics as deterministic, that there is information buried in the gene that is going to deliver an outcome or predict an outcome with a high degree of accuracy. And you're saying right now, at the state of the science, in fact, most of what the gene can tell us is very much a kind of a dice rolling, probabilistic bit of information. Now, is that to say that 100 years from now, we're not going to get more deterministic in terms of our understanding of things? In other words, as we research and get more information about the gene, are some of these things that are probabilistic going to become more deterministic? Or is it more like quantum mechanics, where we're going to find a break-off point in genetics where these phenomena are essentially probabilistic and you're never going to know, but up to that point, you're going to know?
Well, first of all, we're focusing on predictive power of genetics. That's what we're talking about right now. And right now, we're using genetics, even in that probabilistic vein, to find targets for new therapies. So that's going on right now. The genomic revolution isn't as wishy-washy as we're making it sound. It's really helping us with basic science that's going to make difference in the short term. But I do think you're right. I think it's going to take many decades for us to get more predictive with our genetic markers. And it's going to be discovery of more genes, discovery of more variants, discovery of epigenetic phenomena, which means the things that turn your genes up and down and sort of like a rheostat. So there's going to have to be proteomic layering of information on this. The microbiome is going to come into play, all the environmental interactions with your genome. It turns out it's fantastically complicated. And so I do think it's going to take a while to be more specifically predictive.
So a myriad of very complicated states that have to be evaluated simultaneously.
It helps to understand that the scale of this is fantastic, and the stochastic issues in sequencing every one of these 3 billion bases along each and every one of our genomes means that there is a probability of getting it wrong there. Then there's the 5 million variants that we differ from each other, and there's a probability of miscalling that. And then there's interpreting whether that gene really goes with that disease. We know BRCA1 really goes, but a lot of genes we're not sure. Then there's the particular variant. Which of those mutations do you have, and is that one actually cause disease? Then there's the question of whether it's really going to happen in your lifetime. What's the penetrance of that variation in causing the disease? And then there's the question of, can we do anything about it? So we're really struggling in medicine right now because we don't tend to think probabilistically very well in medicine at all. We're like, leeches, and we think that helps. We're really bad at probabilities, and so we're really struggling with trying to layer all these probabilities as we contemplate a world where each of you can walk into our doctor's office with your own genome in hand.
But we're not there, and you've
Not
really
there yet.
convinced me not to get my genome sequenced. But Len, you said you were going to do it. which suggests to me that the strategies of Drunkard's Walk are a way of empowering citizens to understand better some of the probabilities that are out there. How would you say that people can empower
For instance,
themselves?
I was just thinking when we were seeing that nice age, that age breakdown for breast cancer, so your chances are 1 in 8 having breast cancer in your lifetime. Then they start showing in your 30s it's this, in your 40s it's that, in your 50s. Well, guess what? Once you've gotten through your 50s and you haven't got it in your 30s or your 40s, it's not 1 in 8 anymore. It's a little bit less because you've dodged the bullet. That's kind of Bayesian thinking. So getting used to thinking this way, I mean, it helps a lot in medicine. I mean, it helps in business and helps in all areas. But and I was diagnosed with AIDS in the 80s, and these tests were first coming out. And my doctor said, "Oh, I'm really sorry. You're the first one I've had, but the chances of this test being wrong are 1 in 1,000." And I was a little too shocked to be thinking real Bayesian-like. But what happened was, he mistook the false positive rate for the chances that the test was wrong. And I think actually the intro that you saw for 6 minutes
Right.
actually explained that. So, the chances were true. If I had gone in and the doc said to the doctor, the chances before I took the test, the chances of me getting a positive when I didn't have it were 1 in 1,000. But now I had it, the positive. So how do you analyze that? Well, out of 1,000 people, there'll be 1 in 1,000 who get this, even though they don't have AIDS, right? But my chances of getting AIDS, given I'm heterosexual, wasn't taking drugs, et cetera, were about 1 in 10,000. So if you took 10,000 people, you would have one person like me who had AIDS. And if they all took this test, you would have 10 false positives. So the actual chances, what my doctor should have said was, don't worry, the chances are 1 in 11 that it's right. But instead he said the chances are 999 out of 1,000 that it's wrong. And so, trust me, understanding these things is helpful, and you should figure it out.
How long did it take for you to get a second test?
Well, I got it. It's funny. It was an insurance test. So they didn't even tell me. They just said we're denying you insurance, and I had to figure it out. And then they eventually told me why. And then I had to go to my doctor, and then we sent me for another test, and it took I think 2 weeks to get the results of that test. And it was kind of a nightmare, as you can imagine. Yeah.
That's a nightmare. Speaking of nightmares, let's talk about driverless cars for a moment. Alan, let's talk about something that delights us, this idea of driverless cars, and that also scares us because there's so much indeterminacy when we drive. First of all, we're certainly told that driverless cars will be a spectacular new thing. I don't like driving in traffic, but how does a driverless car work, and how is it evaluating the world?
Well, the machine itself, right, the car, is deterministic for the most part.
This is how the
Right, so we'll pause here and I can explain this. The car itself is deterministic. The way, the amount you push on the accelerator and where you drive, that's kind of predetermined in a sense. You expect your car to behave in a certain way. But the problem is the world is totally random, totally probabilistic.
we've noticed.
Yes, indeed. But actually, I misspoke there. It is very probabilistic, but not totally so. There are some things that occur more often than not, and in a given situation, it's possible to determine where to go in the car if you know what's around you, right? You can get through traffic because you're observing the world, and then you act, and the machine acts in a way you expect it to, and then the world changes in some way, so you can react. So one way of thinking about this, kind of an axiom, would be that motion structures sensing, and sensing structures motion. And a driverless car takes advantage of that. So what you see here is a model of the world that the robot has made. Its sensors have detected the cars around it, and also the path that it wants to take, which is the road. It's done that through sensing. But if it were just sitting there, it really would not do as good a job as if it moved a little bit and then sensed again. because what happens is that the motion structuring the sensing lowers, kind of compresses the probabilities of what's actually there. So, for example, if it's going by a parked car, right, the sensor picks up the car, but it goes forward, and the sensor is going to see that that car moved backward because it's parked. On the other hand, if the car you've detected moves with you, then that means that the car is actually moving.
So in a frozen state, the information that the computer gets is there are a bunch of cars around me. They could be parked or not parked, but the motion separates which ones are parked that it doesn't have to deal with so much versus the ones that are moving.
That it needs to pay attention to. Yes, so the idea is that you start with like purely random world. The probability that things are anywhere is kind of just
like
totally...
the West Village, like the way I'm driving in the West Village, yeah.
Yeah, or like my bedroom when I was a teenager. I mean, it's just stuff is could be anywhere. What happens is the car moving and sensing at the same time enables it to narrow the probabilities of what's around it so it can make a decision about where to go.
Now, how does that work in programming? Does a program that takes advantage of probabilistic, indeterminate phenomena actually come to a fork in the road and roll the dice and say this one's likely, or does it actually have a calculation which says this is the best path, or what's it doing?
Well, it could do either one of those things. It depends on what it's set up to do. But all of this is driven by an intent or a goal. It's trying to get from where it is to somewhere else. And that intent informs the action, but also the surroundings inform the action. What it has to do, because the world is so random, is that it chooses the best course of action given how it has sensed the world and the goal it has.
When does the driverless car get to a point where it realizes I'm in a zone where I could really make a mistake here, I should pull over and stop? How does that calculation get made?
Well, if the probabilities, if its best guess is still indeterminate, right? The idea is that these probabilities narrow as it moves on, observing the world. The distribution becomes narrower, and it's going to select as reality the mode of the distribution, the peak value. And normally, we want that to get very narrow as the car is moving along. But if the probabilities are still spread all over the place after it's done its sensing and motion, and it can't just make a good decision about which way to go because it's so random, that's when it has to give up.
So that's the guy who asks for directions.
Right, that's right.
There we go. Let's look at the, what's it called? The kidnapped robot problem, which actually helps us to understand how a chip actually, let's see it go. So here's a robot moving, and this is a sort of statistic likelihood that as it goes through the doors, it could be kidnapped, but it's not. And so those probabilities go up. And it moves for a while. It realizes there's no doors around here, so I'm safe. Ooh, wait a minute. Ooh, I'm a little bit scared here. And there it goes up. There it goes up. All right. Now, at the end of this little sequence, it has a lot more information than when it started. So let's go back and sort of frame by frame kind of go through this and tell us what the computer is doing.
Well, what I'd like to do first of all is describe a situation that most of you have probably found yourself in. The way these probabilities are narrowed down is that in terms of belief, the belief that I am at a particular point in space, that probability is based on what I'm sensing, right? So the probability that I'm here depends on the probability that I would see all of you based on the fact that I am here, right? So my sensing matches what my belief is. So the probability that I have to refer to this because if I could write the equation down, it would be easier to explain. English is not the right language to use for a lot of this stuff, and that's kind of that's what scares people away. The probability that I'm seeing what I am seeing, given that I am where I think I am, okay, times the probability that I am where I think I am given the action that I just took, starting from where I was before this, times the belief that I actually was at that starting point, and that's summed over all the possible starting points.
You're right. English is a bad language.
Isn't it? Isn't
No,
it?
no,
It's
wait
awful.
a second. Wait a second here. I'm looking at your bio. You are a professor of electrical engineering
Yes.
at Vanderbilt.
Yes.
You sure it's not the Divinity School?
Yeah. Well, let me say,
Moses said that a long time ago.
Yeah.
because people in Nashville may see this, I just am going to drop that question completely.
Okay, very good. Sorry.
I don't
But
want
folks in
the
Seattle.
pitchfork.
You folks in Seattle, don't tell anybody you know from Nashville what you just heard.
Yeah,
All right.
I don't need the pitchforks.
So basically, the little robot here is using that equation, right?
Well, let me
Kinda.
give you another example here. And I checked this out myself yesterday. I did some walking around. The hotel we're staying at is at Union Square. So let's assume that you get off the train, you're on the 5, and you get off at Union Square, and you choose one of the exits, and you go out, and what you see is the Walgreens. Okay? So the question is, where am I, based on the fact that I see the Walgreens?
At Walgreens?
You see the Walgreens, okay? So that means one of two things. You're either in front of the food emporium or you're in front of the Best Buy. But it could be either one, right? Now, I'm just assuming you see the Walgreens, but nothing else. I mean, you got tunnel vision. Maybe you were hanging out in the village a little too long that day. But, you just know the Walgreens is there. So you don't know if, in fact, you're in front of the food emporium or the Best Buy. However, then, you see, it's not enough information, right? Just what you're sensing. However, if I believe I was at the 14th Street and 4th Avenue exit and went through there and went up the stairs, then I know that I must be, in fact, in front of the food emporium because that's where that exit leads. On the other hand, if I went out the 14th Street exit that on the south side, and I went right up the stairs, I wouldn't see the Walgreens, so there's zero probability that I did that. If I took a left and went up and saw the Walgreens, well, then that means I'm in front of the Best Buy. So what's happening in that ridiculous statement that I read that describes the equation is that we have to know our belief in where we are is conditioned on not only what we observe, but also what we have done given where we were before.
So there's a memory bit, there's a sensory bit, and that explains who the bald guy with the blindfold was in Union Square last night, coming out of the subway repeatedly. Yes, okay.
Yes, yes.
But it's nice that you solved that experiment. So in the case, we don't need to see the animation again. In the case of the robot, and this is an artificial intelligence kind of
Right.
question.
Yeah, it's a classic one.
The software has to basically combine sensing with maps that are internal,
Right.
and use real time to calculate very, very quickly
Yes.
the probability that you're in a situation where you're getting more information, not less, that you're getting found, not lost.
Right.
And that's not trivial.
No, it's not. And in the video that we just saw, the robot, the kidnapped robot, is the robot that suddenly appears in this hallway. And it can tell the difference between doors and not a door, let's say. And it has, let's assume it's in one of the, classroom buildings, the university. And it has a map of the university and all the halls, but it doesn't know where it is except for the configuration. So here, it's going to see, okay, I see a door, I'm in front of the door, the probability there is going up. Now, actually, the probability is that I'm in front of a door. So each of these should have a peak in front of it, and the stuff between a door wouldn't. Okay, so continue on, and it is now at a different door, which was close. It moved just a little bit, and it's now at a different door. So the probability of where it is now dependent on that motion, and the two doors have a higher probability. Now, if it continues on, right, it's taking a while. This is a longer move. No door there. So it had two doors and none now, but it still doesn't know where it is, because there could be a door right there, or there could be one farther away, and it needs that information. So it continues on a little farther. Okay, it hits the door there. Okay, now if that happens to be unique in its map, that there are just the two, a space, and a third one, now it knows where it is, and as it continues on, it can know where it is as it moves on. So that's the classic kidnapped robot problem.
It's accumulating the information, relating it to the internal map, and then making decisions about where we need to go based on the goal that's been programmed going in.
Now, this is interesting because here the robot knows the map. It has a map. There are many situations where a robot does not have a map, right? All it's got is its sensors and its ability to move. And this is what's called, but the problem can be solved. It's called simultaneous localization and mapping, or SLAM. And the idea is that the robot moves, it senses, it gets an idea of where things are, and it moves some more and observes how those things change. And so it has a probability of being somewhere in this environment. As it moves on, the things that it can sense start moving in ways that are structured by its own motion. It can then start to estimate where it actually is, and so it can simultaneously map the environment and localize itself.
So that's what's going on when somebody comes into your apartment for the first time and wants to see all the rooms and check out the size of the bedrooms and to figure out what your rent is.
Yes.
Yeah. So it's basically checking out the situation, basically building that map through the sensors.
The remarkable thing is that we can do that at all. But what's happened as the theory of probability has become known, this is very Bayesian, right? The fact is that sensory motor coordination is fundamental to living in the world. Now, that may be a well-duh statement, but it actually serves to structure the world mathematically. The fact that we can move and sense, and so we can see how the world changes as we move. And the world, as we see the world, it's going to determine how we do move, right? That idea of the coupling between the agent, which is the person moving, and the world, forms a complex dynamical system, right? And complex dynamical systems tend to form patterns, right? The patterns, so for, the way a flower grows, the clouds and so on, complex dynamical systems form patterns. Our brains are really good at recognizing patterns. Our brains are really good at remembering patterns. So as we move through the world, even though it's random, we can narrow down the probabilities, and the act of moving and sensing creates a pattern that we can remember and compare other things to.
So probability is destiny, in a sense.
It's most likely what's going to happen.
All right, let's see some, since we're running out of time here, let's see some robots that you've been working on. Just narrate us through what these are.
Robo-naut's a puppet, at least it was, and that means you put on a VR glasses and a couple of data gloves, and as the operator moves her hands and looks through her eyes through the VR glasses, the robot reflects that. But it turns out that's really difficult to do. It is so tiring, makes some people physically ill. So my work was in trying to introduce some autonomous behaviors into the robot. And what I did was use the puppet-like teleoperation to go through a particular operation, a particular task, a number of times, and thereby calculate the statistics of what happens during these different motions, and then enable the robot to predict what it should do based on what it saw while it was being teleoperated. And what you saw there with the shaking hand was an autonomous behavior.
Learning.
Yes.
Also learning.
Yes, absolutely.
Can we see the doggy? Because I love to see the doggy.
All right, this is the big dog. That dog's got to learn to kick back. I mean, this is just...
But these are probabilistic calculations that those legs are making
Yes.
to motion and keep the balance.
Well, yeah, there's a lot going on here, right? But it is very much the probability of where it's going to put its footfall depends on how it's moving and what it's seeing.
Here's a question. Jonathan Langdale asks on Twitter, does luck have any real meaning? Is free will an illusion? Anyone want to take that?
Oh, my goodness. I think my time here is...
Yeah. Nobody wants to take that?
Well, we react to a random world in a way that we actually get things done, which means that we are capable of structuring the world and our motions in the world so that we can figure out what is most likely going on. Is that a free will? Well, that's the philosophical question.
Are there lucky people?
Sure.
Are you one of them?
Sometimes.
Yeah?
You know, if there's plenty actually in this town. It's called Wall Street.
Yeah.
You know, if you flip a coin 1,000 times and you take enough people, there are going to be some that get you know, a large number of heads, 1,000 heads, and those are the lucky ones. And then they'll sell you some some mutual funds and and they'll take their $1 million bonuses.
Yes. And the people who get the bonuses are the lucky ones. The
That's
people who
right.
bought the mutual funds are
Are the
not
unlucky
the
ones.
lucky ones. Yeah, there's another name for those people. But anyway, Brendan Rhodes from New York City asks, how can we reach, and this is for you, Mohseni, how can we reach the state of superposition? Is it similar to parallel universes?
Parallel universe is a particular interpretation of superposition. So it implies that every time that a quantum particle split into a superposition of two states, the universe is splitting into that kind of two configuration essentially, and there is a decoherence between these two, so they are decoupled. But essentially, every time that there is a superposition event, the universe splits into that kind of distribution. It means that if you have two outcomes, the universe is split to two various outcomes. So in the Schrödinger cat example, that there is one universe, the cat is alive, the other one is dead. Personally, I'm not a big fan of this interpretation. And a more traditional Copenhagen interpretation of quantum mechanics is that we should not ask, we have a more pragmatic approach of quantum mechanics, and we do not try to say something that beyond what we can observe. And it's quantum mechanics becomes a mathematical formalism for predicting experimental outcomes.
So let's conclude with something that I think interests me about all of this discussion, and that is, in the history of science, you see a movement away from mythological interpretations, sort of faith-based interpretations of phenomena. The experimental method, of course, created a whole new way of describing and looking at the world. And as scientists have moved on the cutting edge of that conceptual change, human beings, have begun to take up the notions of experimental method, rational thought. The conflict between religion and science is all about this uptake of theoretical notions of deterministic science, the rational notions of science, axioms, these sorts of things. Are we reaching a point now where we're about to cross a cusp where, in fact, some of these notions about probability, where our deterministic scientific classical approach is actually giving way to a much more complicated, intuitive, but scientifically based understanding of probability, and that's a whole new world that's opening up right at this moment in history. Would you say that's the case?
Yes, absolutely. The self-driving car shows it. You could not have a self-driving car if it thought the world was deterministic. With Newton's laws describe how everything moves in the world, right? But there's too much going on. So you can't use Newton's laws to figure out what to do next, where to go. You have to look at the aggregate of the way things are moving and figure out what the most likely way is. And so what's happening is the deterministic laws are real, and they work, providing that you've got deterministic evidence to put in the equations. But in the real world, things are random to a certain level. There's noise in the system. And so the possibility of what's going to happen next now has to be modeled in a probabilistic way. And I do think that people are beginning to think that way.
And it affects our identity in terms of how we think of ourselves medically.
Absolutely. Classically, you've been a patient in front of a doctor, and there's that one-on-one person. We know that clinical trials and epidemiology expanded the numbers that gave us data. We're a few years behind the Googles and the other data gatherers of the world, but medicine's definitely moving into the big data era, and genomics in particular, needing millions of people. The President's Precision Medicine Initiative is launching a database of 1 million people, which is huge for us to get all those genomes together and be able to sort out the prior probabilities and make some sense of this to better people's health.
Masoud, are we on the threshold of a fundamentally new understanding in terms of people and their computers and their machines regarding randomness and indeterminacy?
Yes, but the distinction between, again, the classical probabilistic events are, different than the quantum version. We are in the classical world that we experience, and our intuition has been developed. It's becoming increasingly, as the complexity of our life is increasing because of the connections and the essentially augmentation of the technology and computers and mobiles. It becomes increasingly difficult for people to imagine a deterministic kind of path to their life. So they have to essentially make strategies to optimize their life based on probabilistic events. It's like you can essentially hedge, like a hedge fund manager that decides to invest in various different kind of options to minimize risk, and you have to consider, people have to make these hard decisions to consider all possible outcomes that could happen during their lifetime and during the development of their careers, and it becomes increasingly hard to have like this kind of more of a conservative strategies for life. What I'm saying that it's an inherent risk is creeping into our life, and people have to adjust to handle it.
Embrace the risk and be reassured by randomness. That's the lesson from your work, wouldn't you say?
Yeah, I think, we all try to control our lives. We try and make the best decisions, conscious decisions based on how we want things to turn out. We have plans, but a lot of times we tend to undervalue or underestimate the role of luck will play in our future or has played in our past. So we think that whenever we have a success that it's, we pat ourselves on the back, or maybe we get arrogant, and when we have a failure, we blame ourselves or get depressed about it. But in truth, there's a lot more of luck and randomness that feeds into everything that happens to us, and we should just realize that, be humble, and maybe chill a little.
And work hard, and that basically your way to beat the odds is to work hard, not accept rejection,
right? Exactly.
And that's a bit of mathematics as well as psychology.
So it was, I think, Watson, the computer pioneer, who said, if you want to succeed, have a lot of failures. That's because it's all a game of chance, a game of probability. It's all about getting at bats and trying to get that hit. And what you can do is you can try and form those little peaks that were on the graph there and make them in your favor. But when you spin the dial, it might hit the other spot. You can try and improve the chances, but you can't guarantee anything.
Well, I'd like to thank our wizards of odds here, Masoud Mohseni, Leonard Mlodinow, Robert Green, and Alan Peters.